introduce you to Martin Huseman and Joerg Sonnenberger. Both are long-time NetBSD developers, and they will now present us their ongoing question for modern toolchains in NetBSD. Please, Martin.
Thanks, and for presentation technologies. Okay. This all started a long time ago, but the most recent quest we went on started about a year ago when I got set up with the amazingly outdated GCC toolchain on NetBSD WEX. Nothing compiled anymore. There were lots of errors introduced by the buggy compiler, and so we tried to modernize this. And modernizing a compiler in NetBSD is not easy because we have lots of architectures, and we gave up on finding a single one-size-fits-all solution. So we will see what problems we have to solve and what we did in the end and what options we now provide to the users. We have always been pretty reluctant to use the latest GNU toolchain because it tended to be buggy in every .0 version, of course. And as I told you, we have lots of architectures, and testing is not easy. But we had to do something because the only modern toolchain we had was the optional Clang LLVM stuff we had, and that did not support many of these architectures. So we did a big GCC modernizing campaign and also reorganized lots of other stuff, which we will see in a minute. Oh, sorry. Yeah. Besides the compiler itself, we have to do updates to the supporting cast to everything that the compiler requires, like microcode things and exception handling stuff and various support utilities. We also did changes to the C startup code and got away from the one provided by the compiler. Yeah, and until recently, when we applied for this talk, we had a huge list of GCC versions in tree. That was 4.1 for WEX. We had 4.5.4, I think, or 3 or 4, and 4.8 dot something. We have PCC still in tree. Why, we will see later. And, of course, Clang and LLVM. GCC 4.1 is now luckily gone because WEX upgraded to 4.8. And still, this is not enough because we have one oddball architecture that does not work with any of these toolchains. Oh, thanks. And this is work we did not us two alone, but a large crew, and I put them on the slides so they can recognize themselves, but we are not going into details here. Oh, sorry. That's okay. Okay. So let's look at what kind of problem matrix we have to solve. We have like 70 architectures that we build binaries for. As I mentioned, one is not in the set of officially built things we built on the cluster because it has no in-tree toolchain yet. And even if we ignore this oddball, we have, if my script didn't calculate it wrong, 39 architectures. Probably half of them ARM variants because we built ARM in Little Endian, Big Endian, with hardware float, with version 6, version 7, and so on. But beside that, there are quite a few of differences. For some of these, we have options. So we can, for example, on E386 or AMD 64, we can use Clang or GCC alternatively. And for some of these machines, none of these compilers can be used at runtime, which is a big problem. So this is a list that our build cluster generates for each of the builds we automatically generate, which usually happens like every few hours. This is I picked a special one. It's all successes, no failed builds. And you can see some of these architectures down here. And just to give you an idea what we are talking about. You see lots of ARM stuff here. And it ends with wax, and then there's this strange X68K, which is not a typo, but it's a Motorola 68K based ancient workstation, probably only used in Japan, I think. Yeah, the missing one is the PlayStation 2. Maybe someone remembers it. It's more or less a fun project. We used to run on the PlayStation 2 until NetBSD 3 or something. Then we started using C99 stuff in the kernel, and we didn't have a working compiler that could do PlayStation 2 code, which is a MIPS R5900 CPU. And so we had to give up on that port. But recently, somebody else came up with patches for GCC current and integrated support for this CPU in GCC current, and which then became GCC 4.9. And that's the point where we said, hey, we can revive this. And so we did this. And the toolchain is too young to be in base, but we have a package to build it. And but it's external, so it cannot run on the automatic build cluster. That is one thing left out. Okay, but okay, no serious work is going on. Nobody's waiting for PlayStation 2 support. The other thing I already mentioned is the Sun 2 port. Sun 2 machines have like 8 megabyte RAM. They have a Motorola 68K processor, but less than the 68 through 020. So there are strict limitations. They cannot run shared libraries, at least with any of the tools we have. And so we don't manage to build a modern GCC even to the link state editor, because it's just too big.
They have a virtual address space limit of 16 megabytes, which is way too much to fit GCC inside. So.
Yeah, actually we had to fix the WAX port because we could not execute the GCC we built for it. We cross-compiled it and we could not execute it natively. We had to fix the kernel to allow bigger binaries. Okay, Sun 3 is in a similar situation. We can link the GCC there, but if you try to run it on a machine which has like 16 MB RAM, you will have to wait ages, and it will run out of swap no matter what you give it for anything but Hello World. So this is not a feasible option at runtime for this port. Possible solutions for this are pretty easy, and that is also the reason we still have a PCC entry. PCC, if you don't know it, it's a kind of a fun project that Anders Magnusson took. He revived the ancient portable C compiler and made it work. And it's, if you know from DOS times, the old compilers, it's like Turbo C or Turbo Pascal. It's wham, and the code is there. It's really fast. It does not spend a lot of time optimizing. It does not generate that bad code, but it's a toy. And there's no C++ front end for it. So
no usable, at least. There's some beginning of something which might turn into C++ support.
Yeah, somebody actually mentioned C front in that context. I don't want to know. So this is not the idea to give somebody an option to compile things like Firefox or GNOME on a Sun 2. It's nonsense, obviously.
Wouldn't run anyway.
Yeah, wouldn't run anyway. And it's just the idea that we want to deliver some traditional Unix system which always used to include a C compiler. And so we have to ship something. And we will probably end up in compiling it with GCC 4.8 and delivering PCC as a runtime compiler. And everyone who wants to build something can then use PCC to bootstrap whatever and extend it. So no C++, so no Firefox. It's a pain. I don't care for that platform. One thing that probably is not obvious to non-NetBSD dealers is we do allow GPL v.3 code in tree, but with restrictions. We are aware of the strange license and we don't like it and we want to get rid of it, certainly. But we also want to have a modern toolchain, and Clang and LLVM don't work for all of our architectures yet. So we had a big debate, as always, and we came to a solution that we put this code into a separate directory tree. We restrict GPL v3 stuff to basically toolchain stuff, meaning things you likely are not going to need at runtime, or if you are an embedded vendor and have problems with this license, you can leave it out of your runtime stuff. You can use it for your build, but you don't put it in your device. So it's in a special directory, and this worked out pretty well. We extended it to use for other licenses as well, and we have a farm of source external license something stuff, where we import all the external things, and we reach over to this tree from the base tree via makefile includes and path settings and build it from there. Okay.
This is the point where I'll take over. As we mentioned, we have 3 different compiler families. We have GCC, which is GPL3. The last GCC with GPL2 was removed because the one person that really required GPL2 for certain contracts can now use Clang, so that's no longer a problem. We have the option of using LLVM and Clang, and of course PCC. One of the problems we have is LLVM and Clang currently only fully support x86 and ARM. Fully supported means in this case you can build a complete release and don't need anything from GCC for it. PCC currently has a pretty mature code generation for x86. M68K and VEX is on the way, but not there yet. For Clang, you can build mostly usable system on PowerPC. There's one interface in libc which can't be compiled because it uses a union as argument for a periodic function, and codegen support for that doesn't exist at the moment, but very few things actually use it. It's part of the System 5 interprocess communication stuff. And at the moment, Clang compiled Clang on PowerPC crashes on pretty much any input. It's difficult to debug where exactly it goes wrong, but it's mostly a case of bit tender loving care needed. So Spark and Spark 64 are in a pretty similar position, so we hope to have Clang as choice for those soon as well. Well, and there are some very good arguments for using LLVM and Clang. Compared to GCC, you can build one binary of the compiler, and it supports all the platforms without having to rebuild like 90% of the compiler as you would have with GCC. One of our dream goals is to build the toolchain once and be able to compile all the 70 architecture settings with this one toolchain, because the toolchain build itself is like 30% of the complete compile time for a release. So it's a significant problem. Well, yes. you have to do it once for the cross compiler and another time for the native compiler. So we want to avoid that. And one of the interesting features of LLVM is the integrated assembler. Basically, you don't need to call a separate assembler. It's directly integrated in the process of creating object files. And it also allows doing a lot more sanity checking of the input than GNU assembler currently does. This creates some fun for programs that basically want to compile a file to figure out certain structure sizes and so on. And they tend to use inline assembler for that, which is syntactically not valid. And this completely falls apart with the integrated assembler now. So I have plans for rewriting the corresponding tools to use a more sane approach, but it's not that easy. There's also one problem for the initial platform setup. For modern LLVM, you need C++11 support, which is not in any of the currently released versions of NetBSD. So if you want to build Clang on it, you need to install, for example, the GCC 4.8 package to be able to cross-compile it. GCC wants to move in that direction as well, so it's something everyone is going to hit sooner or later. So the primary problem with PCC is that the code it generates is not very fast. If it's simple code, it's decent enough, but anything that really depends on inlining and fancy optimizations is going to see serious slowdowns with PCC. On the other hand, GCC and Clang are mostly on pair when it comes to the performance of the generated code. GCC still has some advantages when it comes to vectorization and OpenMP support, but that's not so relevant for the base system, more for dealing with third-party code in package source or whatever. So the next big goal for us is to get rid of all the runtime components of GCC. There are mostly three of them. The first is common runtime code, which is linked into every binary, and be it a program or a shared library. And that's completely done. We have a mix of pretty straightforward assembler for it, and for MIPS and some other platforms that have too many different ABIs, we have a C stub for part of it to make it easier. The second important component is libgcc. I'm going into more details in a bit, and the third one is the C++ runtime, which we are going to replace with libc++ and libc++RT. More on that later as well. So compiler RT provides routines like hardware division, which are sometimes not present. For example, ARMv4 and up to ARMv6 don't have a divide instruction. So you have to do that in software. And we have very neatly optimized routines for this, which are actually faster than the GCC implementation. So this provided quite a nice performance boost for those older systems. Another example is floating point support. We still have the same float code in libc as the other BSDs have. Yes, no, libc. And we are currently investigating which version is easier to use, and there's one functional difference between, because compiler RT version doesn't support non-standard rounding modes, but almost no one is using that anyway, so it shouldn't be a problem. There are some special cases like Super Hitachi and HPPA, which require a small code fragment to be linked into every shared library, because those functions can't use the normal PLT stuff. That's the so-called millicode. We are not completely sure yet how to deal with it. Historically, those are position-independent code in libgcc.a, which is still pulled into the libraries. We likely will introduce a separate library for them, like libmilli or whatever, and adjust the compiler drivers accordingly. For Super Hitachi, we have the problem that the division functions have special restrictions on which registers they make global. And until recently, it wasn't possible to use a normal shared library function for that, because lazy binding stub actually clobers a register the function is not supposed to clober. We are likely going to just fix GCC definition and make it use a normal code. The only real reason for not having completely switched over yet is we want to preserve the libc ABI. We don't want to do a major version bump at the moment. So we have to preserve libgcc _s, and we have to do it in a way that still works with the symbol versioning used by it. So you can't just create an empty shared library, because everything that tries to link against it will now fail. So what we are likely going to do is use indirect function support, which basically means the dynamic linker calls a function to tell what the real address it should be using in the GOT or PLT is. But that still has to be written. For C++ support, we have a very nice implementation from the LLVM project. It's pretty readable. Well, if you understand C++ and if you feel like dealing with very, very heavy template use. But it's pretty okay for that. It has a nice comprehensive test suite, which is very easy to run. Again, this is something GCC is horrible at, because you need to install some Tcl-based déjà GNU, and it's not properly documented how to do that. And well, once you get it running, it's nice, but getting to that point is difficult. We have the low-level support under BSD licensed. That's code originally written by Pascal, and FreeBSD Foundation and the NetBSD Foundation together basically obtained a relicense so that we can use this. There are some other languages we haven't really decided on yet. For OpenMP, we are most likely going to use the Intel runtime. The big problem of the Intel runtime is the build system is a mess. It needs Perl and lots of little magic that needs to be completely rewritten. The other option would be the GNU OpenMP runtime, but that's going back to LGPL3. Not something we want to do. For Objective-C, there is a free implementation by one of the FreeBSD developers. But at the moment, we haven't imported it into base because outside Apple, Objective-C is basically only used by GNU-Step, and that's something not so many people care about. For Fortran, there's currently no plan for shipping a runtime, and compiler support is still somewhat open. So this leaves one big topic for C++ especially, which is exception handling. There are some other languages that can interact with the runtime, and of course one of the nice features you get is you can create backtraces of optimized C code even if it doesn't have a frame pointer, for example. So for example, in the kernel in DDB we have the problem that AMD 64 normally doesn't include a frame pointer. The ABI says you don't have to. On i386, it's pretty much a similar issue with recent GCC versions because it's much more aggressive about dropping it. So getting the unwind handling into the kernel allows us to more easily produce reliable backtraces. Well, the general approach here is you save the current thread state on the stack, and you go the call chain back on the stack, and for the program counter for each stack frame, you look into a separate table to see if there's basically a catch block. And if there is one, you also match the types, and if you have a match, you execute the cleanup handlers and are done. So for NetBSD, ideally we want to have the Itanium-based C++ ABI on all platforms. There are some variations, for example, how type pointers are stored and so on, but those are relatively small. What we are using is Apple's libunwind, but so heavily modified you will likely not want to run a diff against the original version. We only provide the unwind interface as used in libgcc, for example, and not the second interface of HB libunwind. One of the reasons is namespace pollution, and the other one is it actually adds a significant amount of code which we don't want to have. One huge problem is ARM. ARM has an exception handling ABI which can be nicely summarized as not invented here. Basically, unlike what everyone else is using, they don't use the normal Itanium C++ ABI with dwarf instructions. No, they have to roll their own things. And they do it in a way which doesn't even map easily on the Itanium ABI. For example, Apple uses a different format called compact unwind, which replaces the virtual machine used by dwarf with a description of the common frame layouts. But it doesn't change any of the other aspects because it doesn't have to. ARM is different. And one of the issues you have when you want to use ABI in the kernel is you get references to some functions no one really wants, but it's part of the way unwind data is written. That's annoying. So what we ended up with is patch the compilers to just generate what everyone else is using. For GCC, this is something like 20 lines, including a macro to identify we are not using the standard code. And the platform support in libunwind ultimately is something like 90 lines of C code, most of them copy and paste, and 40 lines of assembler. That's much simpler than the implementation, for example, in GCC for the ARM EHABI. Unwinding on Spark is somewhat interesting because Spark is the only still actively used platform with register windows. Basically, the idea is you have a set of local registers, output registers, and input registers. And when you do a function call, the input registers of the calling function become the other set. Yes, and so basically you are switching the register set, and the old local registers just disappear, and the chip itself has a very large register set with SRAM somewhere, and if there's an overflow because there are too many stack frames, there's a trap, and you move some of them out onto the real stack. That's very nice because it makes function calls pretty cheap, and on the other hand, you have to deal with it for unwinding. So there's a special draft instruction to say, okay, I'm now entering a new stack frame, and the other specialty of Spark is all other instructions save the next address after the call on the stack. Spark doesn't. It keeps the old one, and basically the return is supposed to increment it. So this needs some special logic as well. HPPIA has a similar feature. It stores in the return address the privilege bits. So you can move from higher privilege code to lower privilege code, and the other way around. And you don't have a fixed value for this bit if you are in the kernel, so you have to mask it off. And then there's the VEX. The VEX is very interesting when it comes to function calls, because it's the very definition of a complex instruction set. So what the call instructions on the VEX can do is realign the stack. The entry point of a function says, I'm going to use the following registers, so save them on the stack. And the call instruction looks at this mask and handles it appropriately. The return instruction, on the other hand, will clean up the argument, kind of like the old Pascal ABI on DOS used to do. And the funny part is the return instruction itself doesn't specify how much argument space there is, because it doesn't know it, if you think about printf, for example. So this is actually saved on the stack, and this is something Draft can't really represent easily. What is actually done is you specify the Draft instruction in the caller to say, okay, I have pushed 20 byte on the stack, and during the unwind, you modify the stack pointer accordingly once you have basically emulated the return. The other interesting problem we have for VEX is lazy binding. lazy binding in the old days just left an intermediate stack frame. That's not something you want to have. And one way to deal with it is to instrument the dynamic linker to provide appropriate instrumentation for unwinding. The other one is we can try to clean up this intermediate stack frame. What we actually do in most cases is we basically remove the stack frame, go back to the original caller, and just rerun the original call instruction, now with a fixed address. That's a really nasty hack, but it works surprisingly well. And the other problem we had, both GCC 4.5 and 4.8 created unwind data that's just completely wrong. I have no idea how that ever could have worked. So with that, we are done. Are there any questions? No, in that case, thanks for your attention.